Okay. Uh, so I have uploaded one lecture yesterday night. I think you don't have time to go through that one. Okay. Uh, so I will share the screen. Okay. And so please visit your LMS page. Okay. Then you can find the okay. So this is the content of the LO1. Okay. So I have uploaded 7 lectures. Okay. So please go through all the lectures. Okay. And so if you are not comfortable to go through this lecture, okay, you can use this tutorial. Okay. You can use this tutorial. Okay. So you can try to answer this tutorial by yourself. Okay. The most of the things we have discussed in the lecture. Okay. But some parts we didn't discuss. Okay. For example, these basic things we didn't discuss in our lectures. Okay. But you can try to answer that one also. Then you can refresh your memory. Okay. So uh, so if you are not comfortable of going through that lectures, okay, you can try to answer this question by yourself. Okay. So for that one, you have the reference book. Okay. So all the examples, okay, I get from the reference book. Okay. And I also put the example number also, so that you can find it easily in your reference book. Okay. So I think uh, if you can answer this question by yourself, that will be enough. Okay. That will be enough. Okay. And there are around 17 questions. Okay. So you can try them by yourself. Okay. Or you can try these as a group. Okay. And try to answer all the questions. Okay. Then answer you can keep with you. Okay. So you can refer it for a final examination. Okay. So it will be a note actually. Okay. So so try to answer these questions. Okay. So if you have any problem, please ask me. Okay. You can ask me. Okay. Or you can ask anyone else. And I think you also have some videos. You can find some videos on YouTube. Okay. You can refer them. Okay. So you can use any method you like, you prefer. The only thing is you should be able to answer these questions. Okay. So please try to do that one. Okay. So you can do it as a group. Okay. Then you can discuss. I think uh, 4 hours may be enough to answer all the questions. Okay. Um, so please try to do that one. So if possible, please submit one answer script to me. Okay, then I can correct it, or then I can refer it also. Okay. So if there is any if there is any information need to be added, then I can add it. Okay. So if possible, I recommend you to submit one answer script to me also. Then I can refer and I can verify your information is okay and your note is complete. Okay. So please try to do that one. Okay. Okay. So I think that is related with the LO1. Okay. Then we have completed the LO1. Okay. So at the end of LO1, you should be able to use at least this McCloskey method. Okay, McCloskey method for tabular method, this McCloskey tabular method to solve sum of product and product of some Boolean expression. Okay, and also you should be able to understand the design of a counter. Okay, and you should be able to draw the timing waveform of a counter, of a given counter. Okay, so maybe to the exam I will give it with some logic gates also. Okay. So you should be able to write the waveforms, timing waveforms at each output. Okay, so if you have done this example, I think that will be enough. Okay, you can do that one. Okay, so I think we have write many timing diagrams. Okay, in our lectures, 2 or 3 timing diagrams we have drawn. Okay, and also you should know these things. Okay, the maximum number of flip-flops and modulos, how these are related. Okay, with respect to synchronous counter. Okay, and then you need to know how to design a counter. Okay, how to design a counter less than this modulus 2 to the power n. Okay, 2 to the power n counters we can, it is very easy to design. Okay, okay, if you want to design a counter that count up to 8, you can use 3 flip-flops. Okay, then you can easily design a counter by yourself. Okay, but if you want to count less than 2 to the power 3 count states, okay, then you have to do a design. Okay, so the basic designing procedure is the finite state machine design procedure. You can use the same thing for that one. Okay, so first you have to verify what are the status, what are the required status. Then you have to verify it, how that status are changing from one to other status. Okay, then using that information and the flip-flops you are going to use, using those information, you can make the excitation table. Okay, so using the excitation table, you should be able to design the combinational logic circuit. Okay, so that knowledge you should have. Okay, okay, so I have given some examples. Okay, please try to do this by yourself. Okay, and if you can't do this, please ask me, then I can help you. Okay, we can arrange another tutorial session or something to discuss the difficult things. Okay, then we learn about register. Actually, we have learned about shift registers. Okay, so in the last lecture I have uploaded. Okay, I explained this shift register. Okay, so this shift register is available in our labs. Okay, this IC 74991 register IC. Okay, so I have explained the operation of this register. Okay, and I think if you can explain the operation of this register, that will be enough. Okay, so please try to do that one by yourself. Okay, only thing you have to do is try to answer this question by yourself. Okay, as a group or as an individual. Okay, anyway. Okay. So I think that is enough for LO1. Then we have to move to the LO2. Okay, so in our LO2 we have to discuss about logic families. Okay, logic families. Okay, okay, so let me, so I will refer the node directly. Okay, not the node, I will refer our reference book directly. Okay, I think that will be easy. Okay. Okay, so chapter 5 is the logic family. Okay. Okay, so can you see my screen?
Yes.
Okay, thank you. Okay, thank you. Okay, so okay, so logic families. Okay, so before going to this, before starting this session, okay, can anyone tell me what are the basic electrical or electronic component we have? Can anyone tell me what are the basic component we have? Sorry. Yeah, Prasad, I think your bandwidth is problem. Your connection has a problem and we can't hear you clearly. Okay. So anyway, we know that basic component we have, the most basic components are resistor, capacitor, and inductor. No? We have these component, LRC, okay, and also we have diodes. Okay, we have diode. There are many type of diode available. Okay, diode, and then we have transistor. Okay, we have transistor, and also for a transistor there are many type of transistor available. Okay, so I think these are the basic component we have, no? LRC and diodes and transistor. Okay, currently we are using these basic component for our whole electronic circuit. No? Okay, so you know that, okay, so you know that any electronic circuits, any complex electronic circuits are designed using these basic component, no? Okay, so we can see that these are the building blocks of the electronic circuits. Okay, and you already know that, okay, you already know that basically we have two type of circuits. Okay, basically we have two type of circuits. One is analog circuit, and other are digital circuit. Okay, digital circuit. Okay, now now in currently, okay, in currently mostly we are using digital circuits. Okay, we are using digital circuits. Okay, now the analog, we can't say that analogs are completely out of work or out of range. Okay, still analog circuits are using. Okay, that is because real world is still, the real world is analog. It's not still real world is analog, no? Okay, so we have analog circuitry also for our processing. Okay, but mostly we are using digital component. Okay, digital circuits for our task. Okay, currently we are performing the task using digital circuits. Okay, okay, so I think you know already, you know that the analog means what is analog signal? Can anyone tell me what is analog? Please, someone tell me what is an analog circuit? Please tell me. What is analog signal? What is analog signal? What is the analog signal? Can you hear me? Yeah. Yeah, I got one answer and it is correct. Okay. Continuously varying signal. Yeah. Okay. Yeah, it is a continuously varying signal. Okay. What is a continuous signal? What is a continuous signal? Okay, we have actually a signal called continuous signal, then discrete signal. Okay, we have discrete signal. Okay. The continuous signal means we refer this is also called continuous time signal, and this is also called discrete time signal. Okay, discrete time signal. That is the correct word. Continuous time signal, discrete time signal. Okay. So continuous time means, okay, your time axis is continuous. Okay. So if you consider any time time range, okay, 0 to some time, okay, so all the values are there. Okay, all the values are there. So in this time gap, you have infinite number of times. Okay, infinite number of time points. Okay, so that kind of signal is a continuous signal. Okay, and discrete means you have only discrete value. Okay, that means if you consider if you consider time if you consider a time period 0 to t1, okay, all time points are not available here. Few time points, finite number of time points you can see. Okay, so that is the continuous time signal. Okay, that is a continuous time signal. Sorry, discrete time signal. If you consider a time period t to t1, okay, all the time points are not available. Okay, but you can see some few countable time point between these time duration. Okay, so this type of signal is a discrete time signal. Okay, so discrete time and continuous time classification based on the time. Okay, the time value nature of the time value. Okay, and what is analog signal and digital signal? Anyway, that is your answer is correct. Okay, what is analog signal and digital signal? Analog signal means we are considering a voltage amplitude. Okay, for this classification we are actually consider the voltage amplitude. Okay, so you know that people can be classified using many factor, no? Okay, based on many factor we can classify the people in the world, human in the world. you can say that if we consider the quality of a people, you can say that there are there are good and bad people. Okay. So if you get the fact, the color of the skin, you can say that there are white and black people. Okay. So if you consider the money or property, when you are classifying, you can classify them rich and poor. Okay. So based on different factors, you can classify the human into different category, no? The signal also same. Okay. So based on different property, we can classify the signal into different type. Okay. Different classes. Okay. So based on the time nature, we can classify them into continuous and discrete. And based on the voltage amplitude nature, we can classify it into digital or analog. Okay. So analog signal means, okay, this kind of signal. That means if you consider two amplitude level, okay, this amplitude is continuous. Okay. So you have infinite number of amplitude level. Okay. So here you can see that you have infinite number of amplitude level. Amplitude level. Okay. And if you consider a digital signal, okay, if you consider digital signal, you can see that, okay, you can understand that the amplitude levels are finite. Here you have in analog signal, you have an infinite number of amplitude level, But in a discrete digital signal, if you consider two amplitude level, okay, you will have some countable amplitude level. Okay, maybe 5 amplitude level, maybe 100 amplitude level. Okay. So that if you consider this a voltage signal, you have some countable voltages, maybe 0 voltage, 2 voltage, 3 voltage, 5, -1 voltage, like this. Okay. So you have countable number, finite number of voltage level. Okay. So that is the digital signal. Okay. Okay. Now, can anyone tell me, when we are using electronic circuit, why it is easy to handle this digital signal? Can anyone tell me? The analog signals are hard to process, but the digital signals are easy to process. Okay. So can anyone tell me? Okay. So okay. So think about the storing of the signal. Think the storing of a signal. Okay. Okay. So if you want to store signal in a memory location, so we have studied the registers, no? We have studies about registers. Okay. So there are some registers like this. Okay. In electronic circuits, we have some registers, memory location. Okay. These are memory location. Okay. Now you need to store a signal. This kind of memory location. Okay. So can you tell me, it is easy to store analog signal or digital signal, and why? What is the reason for that one? Can anyone tell me? ඇයි අපිට analog signal එකක් store කරගන්න ලේසි, digital signal එකක් digital signal එකක් store කරගන්න ලේසි analog signal එකක් store කරගන්නවට වඩා කියලා කියන්න පුළුවන්. ඔකට තේරෙනවා, definitely analog signal is hard to store and digital signal may be easy to store. Can you tell me why? Consider the memory of a circuit. Please tell me. Can anyone tell me? Okay, we know that if you consider electronic circuit memory, okay, I think you have learned about Arduino, okay, and okay, consider our computer memory. Consider our computer memory. Your computer memory has a value, no? Your computer memory has a value. For example, your computer has a RAM, random access memory, okay? So it has a size, maybe 4 GB, maybe 8 GB, likewise. Okay, so what is this means? What is this mean? This RAM can store only 4 gigabyte. Okay, only 4 gigabyte this RAM can store at once. Okay, and some RAM can store 8 gigabyte. Okay, and some RAM have 16 gigabyte. Okay, in a server you have 32 gigabyte RAM also. 32, 64 gigabyte RAMs. Okay, so you can see that any memory has a maximum value. No? The memory is not infinite. Memory එක infinite නෑ. It has a limited value, limited capacity. Okay, so all memory has a limited capacity. All memory has a limited capacity. Okay, that means it has limited memory location, limited registers. Okay, minimum register, limited registers. Okay, so it is not infinite. Okay, so if you consider analog signal, say that you have this kind of signal, this is a voltage signal. Okay, so you want to store it. Okay, so what you have to do is that, so you can see that from here to here, there are infinite number of voltage level, no? This one, this one, this one. There are infinite number of voltage level. So you can't store this all the amplitude level or voltage level in the memory, because memory is a limited, but here you have infinite number of voltage level. Okay, so you can't do it. Okay, so the solution is you have to convert this to a discrete signal or digital signal. Then you have countable number of voltage value or finite number of voltage value, then you can store it. Okay, so that is one example. Okay, so when we are going to store a signal, it is hard to store analog information. Okay, because analog information has infinite information levels. Okay, but digital we have finite levels. Okay, so it is easy to deal with digital signal. Okay, so I think you have that idea. Okay, then tell me. Okay, so you can see that now digital, we prefer to use digital circuit rather than analog circuits. No, is that clear? I hope you clear it. Okay, you could understand that. Okay, so we like digital. Okay, we like digital rather than analog. Okay, so in digital we have finite levels. Okay, finite levels. Okay, so most probably digital will have 2 levels, 2 levels or 3 levels. Okay, 2 levels or 3 levels. Okay, so 2 levels may be voltage. Okay, maybe voltage, high voltage and low voltage, high voltage and low voltage. Okay, And there may be another level also that is called high impedance or low impedance. High impedance or low impedance. Okay. So these are called tri-state, tri-state, tri-state circuit. Okay. Tri-state digital circuits, and these are two-state digital circuits. Okay. So if it is a two level or three level, okay, so we can see that we can combine, we can convert this digital circuits into logic circuit. Okay, logic circuit. Okay, so logic circuit also a digital circuit with which has only two levels or three levels. Okay, so if it has two level, we called it two-state logic. Two-state logic. Okay, now we are learning about this. Okay, two-state logic actually. Okay, and if it has three-state, we called it three-state logic. Three-state logic. Okay, so I think it is clear. Okay, so we like to use digital circuits. Okay, and if the levels are, if we are dealing with few levels, it will be very easy to handle. Okay, so that we develop only two-state and three-state logic circuits. Okay, so two-state logic circuits we called two-state logic, and if we have three-state, we called it tri-state logic. Okay, so there are two type of logics circuits: two-state logics and three-state logics. Okay, okay. Now, okay. Now tell me. Uh, These logics, okay, when we are talking about logics, okay, logics, these are comes, okay, these circuit are comes as integrated circuit, no, integrated circuit. So the next problem is, what is integrated circuit? Can anyone tell me what is integrated circuit? So if you consider logic, okay, that means two-state value, okay, okay, two-state or three-state circuit, okay, mostly we can see that those are integrated circuits. Okay, so if you have, for example, if you can if you get the flip-flops, okay, if you get the flip-flops, basic flip-flops, it is as an integrated circuit, it is as IC. Okay, it is as IC. Okay, and if you consider basic logic gates and gates or NAND gate, it is also as IC, integrated circuit. Okay, so what is integrated circuit? Okay, can anyone tell me what is the integrated circuit? I think we have discussed these things previously. Can anyone tell me what is integrated circuit? Okay, so integrated circuit is nothing. For example, let's consider amplifier. Consider amplifier. Amplifier. Transistor amplifier. Okay. Consider transistor amplifier. Okay. So you know that, I think you have learned this for analog electronics. Okay. Definitely. Okay. So we can design a amplifier. Okay. Very easily using a transistors. Okay, and sometimes you should have some resistors biasing resistors, okay, okay, and maybe sometime you will have capacitors, okay. Like this, you can make a simple amplifier using a transistor, okay, okay. So you can see that we have a transistor and we have several resistors for biasing the voltage, okay, and you have some capacitor also to smooth the signal, okay. So if you consider amplifier, okay, okay, so you can design an amplifier using a transistor and several resistors and several capacitors, and you can what you have to do is you have to just connect them appropriately. Then you will have a circuit, no? Then you will have a circuit. Okay, you will have a circuit. Okay, and you know that if you consider this transistor is made with 2p-n junction. Okay, transistor is made with 2p-n junction. Okay, and if you have 2p-n junction, okay, you can fabricate that transistor by adding 2p-n junction. You can make a transistor, and also you can make a capacitor. What have you to do? You have to just put some plates, no? Plates between the inductor, between the conductor, dielectric, sorry, what is called insulator. Okay, so then you can make a resistor, and using a cable or some metal, you can make this resistors. Okay, so if we know the composition of each of this item, okay, we can fabricate them as a one circuit. Okay, we are not going to use separate transistor, resistor, and capacitor. Okay, but you can get the metal, okay, and you can drop some metal appropriately like this, okay, and you can make this item, okay, item with that metal, okay, by appropriately dropping and making composition, okay, different composition, you can make this, okay, okay. So here you can't see separate transistor, resistor, and capacitor, okay. Those are fabricated inside a metal or some material. Actually, not the metal, okay. The word is material. You can use a material, it can be a metal or it can be an insulator, anything, okay. So you can drop different metal and different material with different composition. Then you can make this transistor process and capacitor process, you can make, okay, without actually using the transistor, no? Okay, so you can see that if you consider this circuit, you can't separate transistor, resistor, and capacitor. Those are integrated as a one circuit, okay, one circuit. Okay, nowadays that circuits are very small and we called it chips. We called it chip, okay. So it is an integrated circuit or integrated chip, okay. Okay, so likewise you can develop integrated circuit like this, okay, but it is very, you need a good technology for that, okay. So anyhow we can do it. Currently we are doing it, no? So we have many integrated circuits, okay, and based on the component consist of based on the number of component, okay, based on the number of component, okay, these ICs are classified into different name, different scale. We called low scale integrated circuit, medium scale integrated circuit, okay? Then large scale integrated circuit, so on. Very large scale integrated circuit, so on. Okay, so those are based on the equipment or component included in the chip. Okay, for example, if you consider basic logic gate, let's say that AND gate or NAND gate, AND gate or OR gate. Okay, so you can make this AND gate or OR gate using 2 or 3 transistor and with some capacitor, with some capacitor and resistor. Okay, so these are called low, small. Sorry, this is small scale integrated circuit. Okay, SSI, small scale integrated circuit. Okay, and flip-flops also, I think scale is belongs to scale, small scale integrated circuit. Okay, and we have discussed about counters and registers. Okay, so it has several and NAND gate. Okay, so these are medium scale integrated circuit. Okay, counters and registers. Okay, and if you consider processor, okay, so it is a large scale integrated circuit. And if you consider microcontroller, it may be a very large scale integrated circuit. Okay, likewise, you can have different integrated circuits. Okay, okay. Now, okay, now you can see that, no? So you know that if we have used integrated circuit, we have several advantage, no? We can save the space, okay? And also we have, if we have the integrated circuits for different circuits, okay? If we have integrated circuits to do a specific task, then what you have to do is you can just connect them together and you can go for a higher order electronic circuits, okay? Okay. So using these integrated circuits are very useful. Actually, it has some drawback also, okay? But generally, we have some advantage of using integrated circuits, okay? So now, okay, now we have seen that we like to digital circuit. We have the digital circuit, okay? And we have, so that in another word, we like to logic circuit, okay? Okay, and also we like to integrated circuit, okay? Integrated circuit, okay? So nowadays we are using logic electronics, digital electronics, and integrated circuits for many design, okay? Many design, okay? So I think that is clear for you. Okay, now let's see how these integrated circuits are made, okay? Made, okay. Now, I think we have already know that, okay? We have already know that if you have inductor, capacitor, resistor, and diode and transistor, okay? Using these components, you can develop any type, any kind of electronic circuit, okay? Electronic circuit, okay? So that can be analog electronic circuit, so that can be a digital electronic circuit, okay? So using this also, you can develop digital electronic circuits also, very easy, okay? But using this component, okay? Using this component, if you can develop some logic component, if you can develop some logic component, it will be easy for our design, okay? Because logic, if you have a logic circuits for different tasks, okay, you can directly use them, Okay, using a truth table or excitation table, you can very easily design a logic circuit rather than designing this kind of circuits. Okay, using inductor, capacitor, and transistor and diode. Okay, you can develop circuit. Okay, you can develop circuit. Okay, for example, if you say that you want to develop a circuit, you need to give an input and you need to have a specific output. So if you know what is the input and if you know what is the output, you can develop a circuit according to that one. Okay. Okay. But if you are using capacitor, inductance, diode, and transistor, you should have very, uh, very strong knowledge on these equipment. Okay. How these are working and the response of these circuits, response of this component, you need to know. Okay. So it will be very hard to design that kind of circuit using this basic electronic component. But if you can somehow convert this to a logic circuit, okay, if you can somehow convert this to a logic circuit, okay, so the input is some logic bits, okay, bits, and you have output. Those are some logic bits, okay. So you can get the relationship of the input and output using Boolean expression, no, Boolean expression, okay. Then you can develop a truth table and very easily you can design the circuit, okay. So that for that one, you no need to have very sophisticated knowledge on these equipment, okay. Is that clear? Okay. So it is very important and it is very beneficial if you can use these things, if you can use these basic things, and if you can develop some logic circuit, it will be very useful, no? Okay, it will be very useful. Okay, actually we can do that. Okay, actually here we are trying to learn how we can develop logic using these kind of basic instrument, basic component. Okay. Okay. So now I think gradually you should understand why we need to do this kind of design, no? Because to ease our work, to make easy our work. Okay. So you can use this component, okay, and you can develop some logic circuit, okay. So based on the component you are using, we have different logic families, okay. We have different logic families. We have different logic circuit. We have different logic circuits based on the component we are using to develop that logic circuit, for develop that logic function, okay. Okay, so we can divide using this, based on this basic component, we can classify this circuit into different logic families, okay, different logic families. Is that clear? Okay, so you know that we have several families, no? Okay, so family, you have a family, no? So your family name is followed by your father, no? Okay, so your father gave the name to your family, okay. In the same way, we have some logic families. Logic families means we have some logic circuit, okay. Logic circuit developed using this parent device, okay. So these are building blocks of parent device, okay. So based on this parent's name, these logic families have some word, have some name, okay. So that is very simple, no? I think you can understand. තේරුණානේ කියන එක. මම ඔච්චරලා කීවේ අපි ඇනලොග් වලින් ඩිජිටල් වලට යනවා. ඒකට හේතුව තමයි ඇනලොග් ප්‍රොසෙසින් වලට වඩා ඩිජිටල් ප්‍රොසෙසින් ලේසි හින්දා. හරිද? අපි ඒක understand කරගත්තා storing කියන concept එක පාවිච්චි කරලා. හරිද? එතකොට digital වලට ගත්තාම digital වල තියෙන්නේ few levels. okay? හැබැයි මේවා සාමාන්‍යයෙන් analogs. මේවා analog electronics වලට නේ ඔකට ඉගෙන ගන්නෙ නේ. Not digital electronics. Okay, you are learning these component for analog electronics. Okay, basically these are analog device. These can process analog signal. Okay, but somehow if you want to deal in digital domain, ඔයාට වැඩ කරන්න ඕන නම් digital domain එකේ මෙන්න මේවා පාවිච්චි කරලා ඔයාට digital domain එකට එන්න වෙනවා. නේ? එතකොට ඇත්තටම අපිට මේවා පාවිච්චි කරලා අපිට පුළුවන් digital domain එකේ logic circuit හදාගන්න. අපිට ඒක කෙලින්ම integrated circuit එකක් විදිහටම හදාගත්තා. ඒක IC එකක් විදිහටම හදාගත්තා. හරි. ඒ කියන්නේ මේ LRC අපිට වෙන වෙනම drop කරලා පුළුවන් IC එකක් හදාගන්න. එහෙනම් මේ වගේන් අපිට logic එකක් හදාගත්තා. logic gates හදාගන්න පුළුවන් නම් ඒකත් IC එකකට අපිට පුළුවන් මේවා කරගන්න. fabricate කරගන්න. හරි. එතකොට මෙන්න මේ basic component මේ basic component base කරගෙන තමයි අපි එක එක logic circuit develop කරගන්නේ. හරි. logic circuit develop කරගන්නේ. එතකොට ඒ develop කරගත්ත logic circuit එකට අපි මෙන්න මේවා base කරගෙන නමක් දීලා තියෙනවා. හරි. family name එකක් දීලා තියෙනවා. ඒක තමයි මේ logic families කියලා කියන්නේ. Okay. So I think you can understand that. Okay. Okay. Now there are many logic families. Okay. There are many logic families. There are many logic families. Okay. So before discussing about logic families, okay, I will give you one task. Okay, very simple task. Okay. So okay, consider this circuit. Consider this circuit. Okay. So what are the instruments this has? You have diode. These are diodes and resistor. So you have a diode and resistor. Okay, diode and resistors. Okay. So using this diode and resistor, you need to develop a logic circuit. You need to develop a logic circuit. Okay. So when you are talking about logic circuit, basically we have several basic logic function. That is not function, and function, or function. Okay. And integrating this basic function, you can go for a higher logic function also. That is NAND, NOR. Okay. And also you can go to the XOR or XNOR. Okay. So all these are we consider as basic function. Okay. But these are the most basic function, not N and all. Okay. So these are the most basic function. Okay. But using this function, we can develop this function also. And nowadays we consider this also as a basic logic function. These are also basic logic function. But these are the most basic logic function. Okay. Anyway, all these logic function we consider as a basic logic function. Okay. So if you want to develop a logic circuit, okay, using diode, you have to you need to try to develop a NOT gate using diode, AND gate using diode, and OR gate using diode. Then you can develop other gates also using diode. Okay. So here parent is diode. Okay. To develop these logics, okay, to develop this logic, what is the parent? That is diode, and also maybe resistor. Okay. So you can give them the name diode, resistor, logic. Okay. You can name them diode, resistor, logic. Okay. So here, this is the diode, resistor, logic circuit. Okay. And what is the function of that logic circuit? That is the AND function, no? That is the AND function. Okay. Okay. Can you try to understand by this yourself? Please take 5 minutes. Okay. Try to understand by yourself this circuit in your way. You can refer the maybe the information maybe here. You can read and maybe not. Okay. I'm not sure. Okay. But try to understand this circuit by yourself, how we can develop an AND gate using these two diodes. Okay, please take 5 minutes and try. Try this. Yourself. You can discuss your friend if you need, okay? Take 5 minutes. Okay, I will make you easy. Okay, just consider you give plus volt here. Okay. Let's say that this is equal to 5 volt. Okay, and you are given 5 volt and 5 volt here. Okay, so anyone tell me what is the voltage here? If you give 5 volt and 5 volt, what is the voltage here? Can anyone tell me what is the voltage here? Don't see this, okay? Don't look at this, okay? What is the voltage here? Please tell me what is the voltage here? If you give 5 volt and 5 volt, what is the voltage here? Uh, I think it is not correct. Okay. And just think again. Just think again. Okay. Okay, if you have this kind of, yeah, correct, correct, no? So if you have this kind of resistor, okay, let's say that this is 5 volt, okay, and if the current is not flowing through this resistor, what is the voltage here? If the current is not flowing, that means there should not be a voltage difference, no? That is the basic Ohm's rule. V equal IR. Okay. Please tell me what is, if the current is not flowing through this resistor, tell me what is the value here? What is the voltage here? Just use the Ohm laws. Please answer the question. If you have a resistor and there is no current flowing through the resistor, okay, and here you have 5 volt, you are given 5 volt, but the current is not flowing through this resistor, okay, then what is the voltage at the other end of the resistor if the current is not? Mhm. No. No, just think about the Ohm's law. So you have a power supply. Okay, you can do it in the lab. Okay. Mhm. Next time, try to do it in the lab. Okay. So you have a power supply and you have the plus and you have the minus part. Okay. So connect the plus terminal to a resistor. Okay. And place a multimeter between this and measure what is the voltage here. Okay. And measure what is the voltage here. Okay. So you can see that it is open circuit. Okay. No current is flowing. This resistor is open circuit. This is like this. You are given 5 volt and this is open circuit. No current is flowing. Okay. If the current is not flowing, what is the happen? What should happen? If the current is not flowing, there should not be a voltage drop. No. If this is 0 volt, there is a voltage drop definitely. Then the current is flowing. Okay. Then the current is flowing. Okay. For example, if you ground this side, that means if you connect this resistor N to the other ground port, the minus port, then here it is 5 volt and here it is 0 volt. So you have a current flowing through it. Okay. So it is not 0 volt. Okay. Then what is the value? Now tell me. What is the value here? If the current is not flowing, there should not be a voltage drop. The voltage drop should be 0. This V is a voltage drop, no? This is the Ohm's law. This is a voltage drop. If the voltage drop is not there, Okay, that means if the current is not flowing through this resistor, that means there is no voltage drop. So then what is the voltage here? What is the voltage here? Yeah. So what about others? Yeah, that should be 5 volt, no? Okay, correct. Because, okay, if the current is not flowing through this resistor, okay, there should not be a voltage drop. The voltage drop between these resistors should be 0. So here also you should have 45 volt potential. That is the potential, not voltage difference. That is a voltage. Okay. So the voltage difference is 0. So there is no any current flowing through it. Okay. So here the voltage is again 5 volt. Okay. Okay. Now tell me. Now consider this one. Okay. Consider this one. So if you connect 5 volt here, and here also you are given 5 volt. Okay. So there is no any voltage drop between these two terminals. Okay. So there is no voltage drop. So there should not be any current flowing. No? Am I right? Because there is no any voltage drop. Okay. So the current is not flowing. Definitely. Okay. So the current is not flowing. Okay. So here 5 volt you given, here 5 volt you given. So the current is not flowing through this resistor to here and here. Okay. So if the current is not flowing through this resistor, what is the value here? What is the voltage value here? If the current is not flowing, that means across this resistor, there should not be a voltage drop. Yeah. Okay. That should be 5 volt, no? Okay. That should be 5 volt. Okay. Because there should not be a voltage drop. Okay. Thank you. Okay. So you can see that if you put this 5 volt, and this one will be 5 volt. Okay. Then I put this to 0. Okay. So I keep A at 5 volt and B at 0 volt. Then tell me what is the voltage here? What is the voltage here? Tell me. Okay, just think it again. Is it 0 volt? Your answer is correct up to some level, okay? But just think, is it equal to 0? Or is it equal to 5? Or the voltage between these two? Just think. Just use the basic Ohm law. Okay. And you know about the diode also. This is a very simple circuit. Okay. Please tell me. Okay, you can discuss with your friend, no issue, okay? Tell me the answer. Yeah, you can assume that the diode is ideal. Okay, we will see. Okay, we will see. Okay. Uh, so this is 5 volt. No? This is 5 volt, and this is 0 volt. Okay. So if this is 0 volt, if this is 0 volt, you can see that. Okay. Okay, you can assume that this diode is ideal. Okay, that means there is no voltage drop between this diode. No, otherwise it will have 0.67 or 0.6 volt. Correct? Am I correct? Okay, if it is ideal, the voltage drop is not there. No, as I can remember. Can anyone feedback whether I am correct or wrong? Okay, let's say that we don't have a voltage drop between this diode. Okay, okay. So, so you can see that the current should be go from here to here. No, the current should be go from here to here. Okay. Yeah. So if it is ideal diode, the voltage is zero. No? Here. Yeah, I think it is correct. No, your answer is correct. Okay. If it is ideal, the 0 volt should be there. Okay. So you can see that I think it is clear. No? Okay. Okay. So you know these things. Okay. So if I set this is to 5 volt and this is to 0 volt, okay, this is to 0 volt, okay. So you can see that here and here there is a voltage drop, no? And also you can see that at that time this diode is forward bias, okay. This diode is forward bias, okay. So definitely there should be a current flowing through this path. Is that clear? Okay. So if you set this 0, only this diode is forward bias, okay, and the current is should be flowing through this diode. Okay. Is that clear? Okay. So when the diode is flowing, when the current is flowing through, when the current is flowing through this diode, it is a forward bias, no? No? The diode should be forward bias. Okay. And here, because this is ideal diode, this end also will be 0. Okay. Otherwise, it will be 0.7. Okay. Correct. Okay. Because if the current is going through there and this is forward bias, okay. If it is forward bias, there should be a voltage drop between this. If it is not ideal, there should be a voltage drop between this diode. Okay. So you have 0.7 here if it is not ideal. But if it is ideal, the voltage drop across this diode is 0. Okay, but it is forward bias. The current is flowing. When the current is flowing through a diode, okay, if it is ideal, there is no voltage difference. Okay, this is don't think this with Ohm's law. Okay, the diode is not the ohmic load. Okay, it is not linear load. Okay, can you remember the characteristic of the diode? Can you remember? IR character, so VI characteristic. VI characteristic of the resistor is like this. No, if you increase the voltage, the current is increasing, but it is not in a diode. Okay, when we are increasing the current, when we are increasing the voltage, okay, it is like this. Okay, when we are increasing the voltage, okay, at 0.7, okay, the current is very high like this. Okay, no, I can't remember exactly. Okay, this is the VI characteristic. No, this is like this. Okay, the diode. Okay, so this is not the ohmic. Okay, so when the diode is forward bias, if it is ideal one, there is no voltage drop between the diode. Okay, otherwise, if it is a resistor, there should be a voltage drop. Okay, so if it is ideal diode, this voltage will be 0 and this voltage will be 0. Okay, and if you consider this diode, here you have 5 volt and here you have 0 volt. So this is reverse biased. Okay, so no any effect. This voltage is not affected to here because this is reverse bias. Okay, no current flowing through it. Okay. Okay, this is not a resistor. This is not like a resistor. Okay, that is the things you should understand. Okay, is that clear? So if you set one pin to 0, if it is a ideal diode, this point also should be 0. Okay, and if you set 0 here, this one also here, both are forward bias. Okay, and again the voltage here is 0. And if you put 5 volt here, this one is forward bias. Okay, and again the voltage is 0 here. Okay, so is that equal to AND gate and operation? Okay, So you have two input. You have two input, and here you have the output. Okay. You have two input. Okay, you have two input. Okay, so this is A and B. Okay, and this is the output. Okay, so if you set 1 to 5 volt and others to 0, you will have 0 here. But if you put both 5 volt, okay, both 5 volt, there is no current flowing through any branch. Okay, so there is no current flowing through this resistor, and the voltage will be 5 volt here. Okay, and if it is one, if you set one pin 0, you can see that the current flowing and the voltage here is 0. Okay, so you can see that it is equal to AND operation. It is equal to AND operation. Okay. 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 Now try to understand this one also. Just try to understand this one. Okay. So let's think that this is 5 volt. Okay. And what happen if you set 5 volt and 5 volt here? What is the voltage here? Can you tell me? Now you have to memorize the transistor. Okay. Can anyone tell me, in this case, how this transistor is working? In this case, how this transistor is working? In what mode? Okay. You know that we can use transistor basic for two tasks. What are they? Tell me. Transistor එක අපිට පාවිච්චි කරන්න පුළුවන් වැඩ දෙකකට, basic වැඩ දෙකකට. What are those two tasks? Please tell me, I need the answer, okay? Yeah, very good. We can use it as amplifier and we can use it as a switch. What about others? I think you should all know this, okay? These are the basic things, okay? So transistor you can use as amplifier and you can use as a switch, okay? So tell me, in this case, this transistor is working as amplifier or switch? I think you have done basic labs, no? Here, transistor as a switch and transistor as a. Yeah. Okay, what about others? Your answer is correct, okay? What about others? This transistor is working as a switch or a amplifier. It is working as a switch, okay? One of your answer is correct, okay? It's working as a switch. Okay. So now try to understand this circuit. So if you have this kind of simple circuit, I think you should be able to analyze. Okay. If you have a very complicated circuit, maybe you can't do that. Okay. Maybe we can't do that, but this kind of circuit we should be able to understand. Okay. Okay, tell me if it is 5 volt, what happened? How can you understand this? Okay, what happened if this is 5 volt and 5 volt? Okay, so you can see that, and this one also 5 volt. Okay, so you know that this is VCE and this is VBE for transistor. Okay, and you know that. Okay, I think you should know that if you set this VBE to some value, if you give a VBE voltage, this transistor is switched. So this is switching, this 2-point switching, and current is flowing through this part. Okay, so that is the switching operation of the transistor. Okay, so current is flowing through this. Okay, so if you put 5 volt here, 5 volt here, okay, and here 0 volt, so current is flowing here from here to here. Okay, current is flowing from here to here, and you will have some voltage here. Okay, you will have some voltage here. Okay, and here also you will have some volt. So here it is 0. Okay, so you can see that there is the voltage drop between this voltage difference create. The voltage difference is creating. Okay, the voltage difference is creating between this base and emitter. Okay, so what happened if that voltage difference is more than 0.7? Okay, this is a PN junction. Okay, This is a PN junction, 0.7 or 0.6. What happened? Okay. So the current is flowing through this. It is in switching mode. Okay. So you have a current flowing through this. Okay. So what happens if the current is flowing through this? That means this is as a short circuit. Now this is just like a short circuit. Okay. So voltage here is 0, and at this point also the voltage should be 0 because this is now short circuited line. It is switch. Okay. If you have a switch like this, okay, if you put some voltage here, okay, if you put some voltage here and if you have some ground here, if you switch this, now this is short circuit. Okay. So this voltage and this voltage is equal. Okay. So there is no voltage drop. Okay. So here the voltage should be 0 here. Is that clear? That is the simple switching operation of a transistor. Okay. Okay, you can do this like this. Okay. Okay, please keep remember that when you are at the uh, lab, you can do this. Okay. So get the transistor like this. Okay. Get the transistor like this. Okay. And connect the bulb here. Okay. And you can have a resistor, give a supply voltage here, maybe 5 volt. Okay. You can see that this bulb is not working. Okay. But if you put 5 volt here, okay, you can see that this bulb is lightning. Okay. So that means there is a current flowing through this part. Okay. It is switching. Okay. So that means, okay. So that means the current is flowing through this part. That means this is short circuit. It is switching. This is short circuit. So here it works as a switch and it is short circuit. Okay. And here also it works as a switch and it is short circuited. Sorry, here. Okay. So here it is just like a switch like this. Okay. When you give a 5 volt here, this is short circuit. Okay. So what is the voltage here? 0. And this is short circuit, no? So here also will be 0. And the current is flowing through this. Okay. So the current is flowing through this resistor. Okay. So if you put a LED here, you can see that it is working. It is also working because current flowing through this path. Okay. So you can verify this. Okay. Try to do this in the lab. Okay. These are basic operation of a transistor. Okay. So now I think it is clear now. Okay. Now I think it is clear. If you give 5 volt, 5 volt, you can see that this is biased and the voltage is flowing through this. Okay. Now tell me, if you set here, set 1 to 0. If you set 1 to 0, what happened? You set 1 terminal 0. What happened? Tell me quickly. Please don't take much time. Still this 5 volt is there. Okay. And now this is 0. Still this 5 volt is there. What happened? Quickly. Tell me. Very easy. Okay. What is the voltage here? If you put 5 volt here and 0 volt in other terminal. What happened? You connect 5 volt here and the current is flowing through this. Okay, so here there is a voltage. Okay, it is not equal to 5 volt. Okay, but there is a voltage. Okay, because the current is flowing. Okay, and there should be a voltage. There should be a voltage drop, but the voltage is there. Okay, it is less than 5 volt, but the voltage is there. Okay, so again there is a, yeah, good. Okay, that is the answer. Okay, and the voltage is there. Again there is a VBE voltage, and this switching. Okay, this is switching, and again you have 0 volt here. Okay, okay, then tell me what happened if you put both to 0 0. Tell me. Please don't take time, because I need to discuss something more. Give me another 5 or 6 minutes. Okay, okay, tell me what happened if you put 0 0 here. What is the voltage here? Okay, so if you have a transistor like this, okay, you can have a resistor, you can have some voltage, and you can ground this. Okay, without giving a voltage here, check the voltage between this resistor using the voltmeter. Okay, see what happened. Okay, so very easy. Here it is 0 volt. There is no VBE because this is 0 and this is 0. So VBE is 0. So this transistor is not switch. Okay, so this is not switch. It is in open state mode. Okay, so there is no current flowing through this path. Okay, so there is no current flowing through this path. Okay, so the current is not flowing through this resistor also. So there should not be a voltage drop between the resistor because the current is not flowing. Okay, so if you set 5 volt here, if it is not a voltage drop between this resistor, there should be again 5 volt. Okay, so if you set 0 0, and you will have 5 volt here. Okay, please try to understand that. And also, I think now you can understand this by yourself. Okay, so please try to understand this operation by yourself. Okay, this operation by yourself. Okay, so you can see that here you use transistor and resistor to logic circuit. So we can say that it is transistor resistor logic. Okay, so this logic is we can call because you use transistor and resistor. Transistor and resistor to design the NAND function. This is NAND function, sorry, NOR function. This is NOR function. Okay, so that is the NOR function. So you use transistor and two resistor to develop the NOR gate. Okay, so that is the logic develop. Okay, so you use transistor and resistor. So it is transistor resistor logic. Okay, okay, here you use, this is NAND operation, and here you use diode and transistor. The main components are diode and transistor. So this is transistor diode logic. Okay, and you can see that you can use it. There are many transistors used. Okay, no need to try to understand these circuits. Okay, because actually here also all transistors are working as a switch. Okay, so you can check one by one what happened to the voltage. Then you can understand the operation here also. Okay, but no need to try if you don't have time. Okay, But if you have time, you can try to understand this one also. In the same way, we have understand that simple circuit. Okay. So you can see that several transistors are used. Okay. So here, the main components are transistor. Okay. So this is called transistor logic, TTL. Okay. And this TTL is the most popular one, popular logic family. Okay. And there are other popular logic families are there. Okay. And this TTL logic families are fabricated as IC. Okay. These TTL logics are fabricated as IC. Okay. So currently we use this TTL logic families. Okay. As IC. Okay. So sometime some NAND gate we are using maybe a TTL logic family. Okay. That IC is belongs to TTL logic. Okay. And you also keep remember that the previously we talked about diode resistor logic. Okay, these are not used to fabricate the IC. Okay, so these techniques are not used to fabricate the ICs. Okay, so there are not any ICs belong to this logic family. Diode logics, diode resistor logic. There is no any IC currently available. Maybe historically also not available. I'm not sure. Okay. And transistor resistor logics also we are rarely used. Okay. I hope we don't use. Okay. Mostly we are using transistor logic and CMOS logic. Okay. And there is other logic family also. Okay. So we will mainly focus our study on TTL and CMOS logic families. Okay. 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 And another thing is, so you know that different family has different characteristics, no? Different qualities. Okay. Some families are rich, some families are poor. Okay. So in the same way, these logic families also have different characteristics, different quality. Okay. So normally, if we okay, if we consider our family, we normally categorize our family based on our class. Okay. Maybe based on our property, maybe based on our caste. Okay. So different based on your attitudes. Okay. You can have any parameter to classify or name your family. Okay. To characterize your family. Okay. In the same manner, these logic families are also characterizing. Okay. But for that one, we are using some important parameters. These are the parameters we are using. Okay. High level input current, low level input current, high level output current, high level output current, those things. Okay. So in next lecture, we will try to understand these things, these parameters. Okay. And we will see different family has different value for this parameter. Okay. Okay. So try to read this by yourself and try to understand by yourself. Okay. To read this, you should have one very important thing. Okay. So you can see that if you consider a logic gate, logic circuit, it has several input. It has several input and it has some output. It can have some output. So you have input and you have output. Okay. Okay. And you know that if this is logic, okay, there should be a high voltage and low voltage. Okay. High voltage and low voltage. Maybe high voltage is 5, low voltage may be 0. Okay. So different parameters can be can be defined. Okay, for example, when you give a high level to input, okay, there can be a input current, okay, that can be go inside or that can be come outside. We don't know. Okay, okay. So there can be an input current for high voltage input. Okay, and low voltage input also there can be a input current and output current. Okay, so there can be a input current for low voltage, there can be input current for high voltage. Okay, in the same manner, if you consider output, okay, if you give a high value, okay, and at the high value you have some output current at low level and also output current at high level. Okay, and also if you consider voltage, there can be a maximum high voltage and minimum high voltage and maximum low voltage and actually minimum low voltage. Normally not minimum low voltage, okay, but there can be. Okay, so likewise you can define many parameters. Okay, and also you can define what is called noise margin also. Okay, so so we will stop here. Okay, so I want you to read this by yourself. Okay, read this parameter by yourself. Okay, and try to understand it by yourself first. Okay, okay, so we will stop. Before that, do you have any problems? The things we have discussed today. If you have any problem, you can ask me. Okay. So anyway, thank you for participating. I will be here around another 5